There was a pioneer ecologist in the 19th century named John Muir, who was largely responsible for why the United States set aside so many national parks like Yellowstone. To me, John Muir is most famous for his observation that when we try to pick out anything by itself, we find it hitched to everything else in the universe. This is especially true in taxonomy. When I do videos on taxonomy, I like to use Wikipedia's dendrograms because then you can just select that one little section of the whole tree of life that you want to see, and they include thumbnail illustrations so that everyone can more easily follow along without getting lost among the big unfamiliar words. Thumbnails would be useless in an all-encompassing cladogram like the Phylogeny Explorer project, but they're very helpful for this type of instructional video, where we're usually only talking about varieties of easily recognizable animals. The problem with Wikipedia is that when you start on one chart and you want to go into another connected one, like maybe you want to explore one of their subsets, they often don't match. And consequently, whenever I've had to use Wikipedia's dendrograms, I've usually had to correct them, sometimes in several places, especially when I try to link one to another. So why are they different? Why don't they all match? Now, one reason is that not every chart is up to date. For example, this one may be based on a concept from 1998, while this other one was revised by a better method that was implemented in 2015, because science changes in accordance with new information. That older one is different than this new one because of a number of corrections that have been made since then. Science is a self-correcting process. Now, that is not to say that science was necessarily wrong back then. The endeavor of science is a lot like playing a game of 20 questions. You've got the basics down and you're honing in on the final answer. You may not yet know what that final answer is, but you know what you know, the answers you've already gotten. You're not wrong about those. So you take the facts, everything you know to be true so far, and try to understand how they all work together. The facts are the facts. They don't change. They remain as they always were, even if we discover new facts. But how to understand all of them together can always be improved. Science in general, and evolution in particular, is not a belief system, because the goal is not merely to believe whatever you're told. The goal is to improve understanding, yours and ours. Thus, science is an investigation, and you're welcome to take part in that, where you gather your information, then analyze and compare testable hypotheses to see which ones do a better job of accounting for more of the data without contradiction. It's best to try to weigh multiple hypotheses whenever possible, or at least allow for that possibility, rather than just following the only one you know or like. It can't be subjective either. You've got to be able to show your work, and not just to your mom or to your friends, people who don't know enough about this matter and who are all just going to agree with you anyway. No, you've got to let the experts check it over, even those who may not like you, even those who don't want to agree with you, until they can say that, well, I can't find anything wrong with it. Then you can say that you did good. You may even change their minds then, too, when they'd have to say, yeah, I didn't like their idea at all, but I've looked into their arguments and evidence, and I think they may have a point. That's how it works. That's the process of peer review. That's how scientists can change their minds even when they didn't want to. No one can ever prove you're right, because that's against the rules. But anyone might prove that you're wrong. And there are lots of ways to be wrong. So don't ever say that something is true or the truth until or unless you can show the truth of it, meaning the body of objectively verifiable facts and evidence to back that up. Because if you don't have that, you don't have anything. Don't tell me that something is so like you know it is when you don't. Because that's just story time, blind, baseless speculation, also known as make-believe, and we don't care about that.
Just the facts, ma'am.
So when you're doing science, consider different models of how this came about or how it all works together. Maybe figure out a different structure or concept in your mind to test it out and see how well it works. Let's see, the way they told me was like this, but that only works for this couple of things, not for the rest. Maybe it's like this? That would account for this too, but not this other one. What would account for this other one too? What if it was like this? That's it. That works for all of it. Everything. The reason science can never prove anything right is because even when it is right in one way, it can still be wrong in another. Look at different models of atomic structure, for example. Dalton's model of the atom from way back in 1803, Bohr's model from 1915, and the quantum model in vogue today. They still teach all of these in school because they all have practical applications. So we know they're all accurate to some degree. Even though they contradict each other, they're all different, and none of them are perfect. We just need to figure out the one way to visualize it that explains all of it. Taxonomy was once the same way. Ye old Linnaean ranks worked okay up to a point, but the concept of monophyletic clades, which only became popular in the last couple decades, works a lot better. And that's a slightly different concept. So some of the names have changed, and the structure was reconfigured a bit to make it more accurate. Not all of the charts on Wikipedia got that update, and that's one reason why they don't all match. If I used Wikipedia for this video, talk about the emergence of arachnids within Arthropoda, there would be too many corrections needed just to start with. So this time I'm going with a peer-reviewed phylogeny instead, one that has thumbnails so everyone can still tell what we're looking at. But even this one is limited for a couple of reasons. One, it's a genetic study, so it's only able to include living groups, things for which we have DNA. There are a few extinct clades in the fossil record that we can't get DNA for, and therefore they won't be in this illustration. But maybe I can still point out where they would be based on morphology. The other problem is that the people who did this study didn't analyze every genome for every arthropod alive today, because that's impossible. There are far too many, like 1 million of them, and who's going to pay for all that? So they only did the certain few that are listed here. Look at Onychophora. This chart shows that they sampled 3 species, each from a different genus, but there's at least a couple hundred species of these things still alive today, to say nothing of the whole other order of these that are only known from fossils. If you remember the first episode of this series, these represent the most basic form of arthropods. Now look at the one with the butterfly. This is Pancrustacea. That means all crustaceans and all insects viewed as a single combined clade, separate from myriapods. Because if you put these two together with myriapods, that would be Mandibulata. Pancrustacea is represented here by a butterfly, but we can already guess that not all of the 7 species listed here would be butterflies. In fact, none of them are. Instead, we have a fruit fly, a beetle, cockroach, springtail, a water flea, a shrimp-like crustacean, and a parasitic louse that lives on fish. Each of these 7 species represents a different taxonomic order, which may contain hundreds or thousands of individual species. And these are just a sample of all those groups to represent them all collectively. Because, as this and every other study of comparative genome consistently reveals every single time, everything in this box is more closely related to each other than they are to anything else in the rest of this chart. So why are Pancrustacea represented by a butterfly? Because a butterfly makes a distinct silhouette for the thumbnail. Butterflies are insects, and half the sampled species are insects too. Of course, there are other, more comprehensive genetic studies of Lepidoptera that show precisely where moths and butterflies and caddisflies are nested within hexapods, insects. But even this chart is just a sampling, because there's only a couple hundred species listed here, representing at least 180,000 known species in reality. So the reality is 1,000 times bigger than even this chart. And that's just the things that are still alive now. We know that way more things have lived and died in the past than we have less today. We started this series exploring Arachnomorpha by talking about trilobites and aglaspids and a number of other things within the clade of Arthropoda, which, despite the fact that it includes a couple dozen taxonomic orders comprised of tens of thousands of individual species, every last one of them went extinct a long time ago. So we don't have DNA for any of them. Thus, they're not on this list. And then we move to chelicerates with the same situation. All the eurypterids and most other stem groups are entirely extinct, so we don't have DNA for any representative members alive today. Therefore, we can't put them on this chart either. What we do have, all we have left of chelicerates outside of arachnids, are just a few sea spiders that aren't spiders and a handful of horseshoe crabs that aren't crabs, representing a tiny percentage of what there once was, including sea scorpions that aren't scorpions that we only know about from fossils. And now we're getting into Arachnida, the taxonomic class that includes spiders and several other similar things. Before we get into their molecular phylogeny, let's recap their fossil morphology. In earlier episodes, we saw that the dawn of arthropods was in the form of walking worms with repeating pairs of legs, and that the legs necessarily became hinged and segmented when they developed exoskeletons. Then, both in Arthropoda and as we moved into Chelicerata, we saw a change in the arrangement of legs, resulting in a radiating array, which we now recognize as the arachnomorph. In one subset of Arachnomorpha, Planeterga, we see development of the abdominal area dragging behind the radiating cluster of legs. This is different from other chelicerates like horseshoe crabs that don't really have an abdominal area to speak of. And this body plan typically ends in a segmented tail with a pointed telson. These were the Eurypterids, known as sea scorpions because they looked so much like scorpions. The difference between sea scorpions and true scorpions, or the difference between Eurypterids and Arachnids, is slight. Unlike insects, whose bodies are divided into three parts, a head with antennae, a thorax with 6 legs and maybe some wings too, followed by the abdomen, arachnids are divided into just 2 parts, front and rear. The cephalothorax, where the head and chest have fused into one assembly, as distinguished from the abdomen. The head area has no antennae, but they typically do have pedipalps in addition to 8 walking legs, which is the most important difference between them and Eurypterids, for whom the number of walking legs was variable. But none of them had 8 legs plus a pair of pedipalps. Eurypterids were almost arachnids, and indeed the earliest arachnids known to science looked like Eurypterids. This one is one of the earliest scorpions ever discovered, back in 1885, and it was initially classified as a Eurypterid, because, to be fair, it's not all there. They called it Proscorpius, implying that it was a protoscorpion, like the form that came before true scorpions. However, it was later realized that it is a true scorpion, just not a modern one. It's one of several primitive forms that are now known as mesoscorpions, a more primitive form than neoscorpions, the newer models like we have today. There were a number of reports in the last few years that this incomplete fossil of Perioscorpio was an ancestral scorpion and the oldest scorpion known to science, dating back to at least 436 million years ago. But further analysis now says that it's not really a scorpion, that it's apparently a much more primitive stem form, not just basal to scorpions, nor even more primitive than sea scorpions, but basal even to the split between Mandibulata and Arachnomorpha, meaning that this came from a side branch that diverged even earlier than trilobites. And since it's not really a scorpion, then it's not the oldest scorpion. The first scorpions appeared in the Silurian period a little over 400 million years ago, and they lived alongside most of the Eurypterids that we talked about in the last episode. In fact, this one, Paleoscorpius, was found amongst a cache of Eurypterid fossils. The mesoscorpions are this first generation of Silurian originals, including Dolichophonus and Petaloscorpio. These are the oldest scorpions known to science, and they are more primitive. For example, arachnologist Andrew Jerram studied every fossil scorpion that was known by the end of the 20th century, and he produced this list of differences between the plesiomorphic state of the mesoscorpions and the derived state of the neoscorpions. Even here, there are transitional forms. For example, Aramuscorpius is the oldest fossil scorpion bearing the anatomically modern walking legs, capable of bearing the weight of the animal by displacing the weight of the surface on a footprint, whereas more primitive scorps had stubby legs ending in points without feet, like crab's legs. And what we usually see in transitional species like this, or from this time, are adaptations for the move onto land. And one of the things we're looking for is like how they altered the method of fertilization by passing a spermatophore in courtship, and how they probably adopted laying their eggs on the shore, like horseshoe crabs do, where I think all modern scorpions now give birth live. One of the things we see in fossils is that once they could walk on land and effectively live on land, because scorpions are the first animals in the fossil record to become fully terrestrial, how did they adapt to breathe the air and subsequently lose their gills, just like our own ancestors did? Silurian scorpions must have lived in the water, since their fossils have gills, but by the Carboniferous period, 50 or 60 million years later, such features are no longer found. Instead, Pulmonoscorpius is the first one to show the presence of book lungs like modern scorpions have, covered by protective plates. So they were probably land dwellers. Meanwhile, its contemporary, Waringoscorpi, has these distended gills, if that's in fact what they are, assuming that they were perhaps readapting to water, because they were equipped with book lungs too. The book lungs and tracheal tubules that scorpions and some spiders use to breathe are apparently derived from ancestral epipods, essentially gills. If that is the case, then this forms the basis for the evolution of tubular trachea in derived spiders and apulmonate arachnids. As some people said that scorpions never evolved, that they were always exactly as they are, unchanged over all this time. Yet there are dozens of different species of scorpions known from fossils, and there are a couple of thousand species of scorpions alive today. And so much has been written about their evolution that I could do a whole episode just on them, but that would only appeal to a fringe niche of arachnids. I need to show other arachnids here too, but I needed to start with scorpions for two reasons. One is that their body plan illustrates precisely how every other arachnid could be related to that, because while some uneducated laity say that scorpions have remained unchanged all this time, some entomologists argue that every other arachnid evolved from them. And the other reason that we had to start with scorpions is that they were the first, the pioneers of this whole group, at least according to fossils. Genetically, it's a slightly different story, one that begins with animals that are usually too small to fossilize. Remember that the larger an animal is, the more easily it will fossilize, and scorpions were much more readily recognizable than some of the smaller arachnids were. They're generally larger too, especially way back then. I mean, I've had scorpions as pets before, little ones of course, because that's all we can get anymore. But can you imagine keeping scorpions like that? They were this big? I would. That'd be amazing.
Like a lobster.
So, do we follow their fossils or the phylogeny? We can't just look at one data set, the one we know and like, and ignore the rest. And despite the close association of sea scorpions and true scorpions and the commonly held belief that was so often repeated that one evolved directly from the other, the most basic and primitive arachnids, at least according to this chart, are a bit more spider-like. Yes, within Eurypterids there were a number of things that looked an awful lot like scorpions, but there were others that looked like spiders and such too, and not all of them were big. Nor were they so easily recognizable, especially considering how many of these fossils were discovered in the 19th century. And no one would have likely noticed fossil mites. Even if there was a fossil there and you were lucky enough to pick it up and look at it closely, the detail would usually be worn away by erosion so quickly on something so small that there wouldn't be anything left to see. So it's better to trace phylogeny by the genome whenever we can. But in this case, we're going to weigh both data sets to see whether they can be reconciled. Like most cladograms, the one for arachnids begins with one main fork leading into two fundamentally different types. And we'll start with two superficially similar generalized forms, apparently basal to all arachnids, at least genetically, because that's how evolution works. The beginning of any two seemingly distinct groups have at their root ancestral forms that are very similar to each other. Small changes accruing more changes over time. That's what it is. And both of these look like spiders, but with whip-like segmented tails. Although to the untrained eye these may look a lot like each other, they actually belong to different groups representing either side of the deepest division within arachnids. Looking first to the palpagids, or to the side where they belong, the top half of arachnids on this chart, I'm going to call these apulmonary arachnids, and you'll understand why in a moment. Palpagids weren't included in this study, but solifugids were, and they're a sister group. Solifugids are like a bigger, more metal version, just without the whip tail. They're a taxonomic order with at least 1,000 different species. I've lived in the Sonoran and Mojave deserts, so I used to see these all the time. We called them sun spiders. And you've probably seen them too in pictures from Iraq, where they're often called camel spiders. But as you can see, they're not really spiders. Those are not fangs, though they're almost fangs. Those are really butch chelicerae. And they're not venomous, but they sure look like they are. And these guys have the attitude to back it up, so that most people just back away cautiously. And this puts us in the middle of two subgroups as they are depicted here, where the more basal primitive forms are on top, starting with Racinioli. Now, we have these in Texas. I've seen them, but they're not really well known, and there's not a lot left of them either. Only a few dozen species, and all of them in just one family. They're called hooded tick spiders, though they're not spiders. They're closer to ticks, but they're not ticks either. They are hooded, though, in that their chelicerae are covered. To keep them sharp, I guess? I don't know. Their bodies are divided into two halves, the typical form of arachnids, but they're missing their pedipalps altogether, and they don't have eyes either, although their fossil ancestors did. And according to this study of their morphology, they're closely related to another extinct group called Trigonotarbida. The next group down are Apiliones, technically known as harvestmen, but more commonly known as daddy longlegs. At least that's what the kids called them in the trailer parks I grew up in. I also heard that their venom was more deadly than that of a black widow, but that it didn't matter because their fangs were too short to get through human skin. Of course, the truth is that they don't have fangs or venom. They have tiny little chelicerae that would indeed be useless against our skin. The next group is Acari, a subclass of ticks and mites. Like the hooded tick spiders, they don't have pedipalps either. So that must have been a derived trait inherited from a common ancestor. At first, they lost their tails, and then they lost their pedipalps, and then they became so small that they lost the distinction between the cephalothorax and the abdomen. They're so tiny that everything is squeezed together into one room now. Otherwise, you know what? The less said about these parasites, the better. Just thinking about them makes me itch. Now, the other side of the arachnid family tree has a formal name. They are a single clade, strongly supported by both molecular evidence and derived synapomorphies, specifically a set of book lungs, which are retained in most of them, including the other spider-looking thing with a whiptail, Schizometa. Whereas, if we look to pseudoscorpions, they kept the claws but lost the tail. I mean, these things are scorpions just without the tail, right? If there is a link between arachnids and eurypterids, as seems there should be, then claws like these could have been inherited and subsequently lost or modified by some descendants and retained by others. And now we get into true scorpions, who kept the claws and the tail, traits that all of these others might have had at some point in their past. There's no way yet to know that, either from fossils or genetics, but it is possible, and if so, that would reconcile both data sets. There are only two features that every scorpion has and that only scorpions have. Only two features that are not shared with any other arachnid. One is the stinger at the end of the tail, of course. That's the one thing that makes it definitively a scorpion. Other arachnids have the segmented tail just without the stinger. Some eurypterids had the pointy bit at the end, but they couldn't use it very well for stabbing, not amidst the resistance of the water they lived in, especially not the way they were built. The other uniquely scorpion feature are the pectins, a pair of comb-like organs on the underside that scorpions use to both feel and sort of taste the ground beneath them, which also helps them detect pheromones to identify mates. If the ancestor of all arachnids was what we would call a scorpion, then it should have had this trait, and that trait must have been the first one lost in all subsequent clades. However, I personally suspect, and I'm proposing a testable hypothesis here, that the last common ancestor of all arachnids was not quite a scorpion, or not yet a scorpion, but that it looked more like a scorpion than a whip-tailed spider, in that it had a segmented tail ending in a pointy telson, just like eurypterids had too, even if, like eurypterids, it wasn't able to use that tail as a stinger. There is sufficient evidence that scorpions made the move onto land, yes, but I suggest that they weren't the only lineage of arachnids to do so, that there was a precursor, perhaps the common ancestor of apulmonary arachnids like ticks and mites and daddy longlegs, something like that, something like a palpigrade, an offshoot of the lineage leading to scorpions that also made their way onto land, just as some eurypterids eventually did, as well as insects too. Although, I must admit that I made a similar prediction 15 or 20 years ago where I foolishly proposed that a fossil would be found that was intermediate between scorpions and Mixopterician eurypterids. And people tried to explain to me back then what was wrong with that, that you needed more than a superficial resemblance, that it wasn't enough that if they look familiar if you squint their eyes from a distance, that it's the essence of the thing that matters. But yeah, some of us have to learn the hard way. The transitional species I'm predicting now would not have had pectins, because I think that feature didn't develop until true scorpions. It would have had claws, but again, they wouldn't be like those of true scorpions. I think they would have been more primitive, like the type of claws seen on Megachiera or Codimyrus. And why do I say that? Because those are the type of claws we also see on whip scorpions, also known as vinegaroons. They represent another 100 or so species from a taxonomic order that I think is pronounced Europygi.
What'd you call me?
We have one of these as a pet right now. They're closely associated with another more spider-like order, Amblypygi. That's another 155 species of tailless whip spiders. These are typically larger than most real spiders, and some of them have different types of grasping claws, quite a variety of grasping claws. I want to get one of these as a pet too, but for an odd reason, because I think they're such freakishly ugly, nightmarish monsters that there's a certain charm in how horrible they are.
Do you like it?
Like it? Why, it's absolutely hideous!
Before we conclude this list, I should add that there are a couple of extinct orders within Tetrapulmonata that, of course, were not part of the genetic study, but that should be remembered here. They include Haptopoda and Eidmonarachni, both from the Carboniferous period, and they are both essentially armor-plated spiders, complete with knife-like fangs. Now, how did their chelicerae become fangs? Well, we can see that illustrated by Amblypygi. Look at their impressively large chelicerae. They had 2 points to pinch together, but they lost one, so they can't grab anything anymore. All they can do is stab it. And since the chelicerae of practically every arachnid is already lubricated with digestive fluids, rather like saliva, then it's almost inevitable that if their chelicerae can no longer cut up their food, that it would soon have poisonous proteins empowering their bite, just the way snakes evolved their venom.
I don't like spiders and snakes.
And finally, there is one more intermediate fossil form that we ought to mention, Urarachnida, which is another part scorpion, part spider, dating all the way back to the Devonian period, nearly 388 million years ago, which I think is roughly about 50 million years after the first scorpions. We'll talk more about these in the next episode, because we started with arachnomorphs and focused on chelicerates, then we zoomed in on arachnids, breezing over all of these other groups, everything except for spiders themselves, which is what the next and final episode of the series will be all about.